So now we are going to do some problem on this digital electronics. Okay, the question is without reducing convert the expression to NAND logic. So here we are given this as A plus B and it with C plus D. Four variables we have A, B, C, D. So we need to draw four lines as the input lines. This is for A, this is for B, and this is for C and D. So we name the lines. This is A, B line, C line, and D line. So without going directly for this NAND logic, first we will be having this expression implemented using basic gates. Okay. So first we'll do it using basic gates. Then these basic gates will be converted into NAND gates. That is the NAND logic. So first we realize this function A plus B. So this is our function. So we take the connection from here. We take the connection from this A and then we take the connection from this B. A plus B, so it is our function. Similarly, we go for the C plus D realization. So C and this D are combined using plus, right? That is our function. So we take the connection from here, C, another connection from here, the D, then the OR gate is, then these two, this one and this one are combined using this dot product here, right? So it can be implemented using AND gates. So this is your output. So this we have done using this basic gates. Now we go for implementing the same using NAND gates. So how to convert this basic gates into NAND gates? For that you should know that this OR gate, suppose if you have an OR gate, that OR gate can be converted into NAND gate by having bubble here. Okay, means this bubbled OR is equivalent to NAND gate. Bubbled OR is equivalent to NAND gate. Similarly, if you have an AND gate, if you put an bubble after this AND gate, you'll be getting this NAND gate, right? So the same technique we are using, but without affecting the functionality, right? So if you add one bubble here, before that you should have an inverter. Then these two effects get cancelled. The same OR gate effect will be there. So here also you have a bubble, so you need to put a inverter here. Okay. Similarly, here we have included one bubble, that means it is an inverter. So to cancel this effect, we need to put an inverter here. Okay, then these two get cancelled so that you get the AND gate function. Okay, so this is how we are going to do the conversion. So I add the bubbles here. Bubbled OR is equal to NAND. So in order to cancel this effect, we are going to have the NOT gate or the inverter. Here also we have this bubbled OR. So to cancel the effect, we have this. So we should have this bubble effect cancelled by this inverter. And I'm going to include this bubble after this AND gate to get the NAND gate. So here I have to include one inverter. That's all. Okay. So after having this, I can replace this symbols with the NAND gate alone, right? So I'm going to delete this. Instead of this bubble door, we can have this NAND gate. This is your NAND gate. Similarly, here also we are going to replace this bubble door. This is called bubble door. Okay. So what is this? And what is this symbol? This indicates inverter, or we can call it as NOT gate. Similarly, replace this inverter. So simply, if you have an inverter like this, instead of this inverter, you can put this as simply a single input NAND gate. Both are equivalent, right? So I'm going to replace these two inverters with the help of single input NAND gate. That's it. Here we're going to replace it using single input NAND gate. Now going to this side, here also we can replace this. This is NAND gate followed by a single input NAND gate. So this is your, so now this is your output. Output is nothing but A plus B into C plus D. So here we have implemented this expression using only NAND logic. So how do you actually write the expressions here? You see, This is taken from this A. So after NAND gate, it is acting as an inverter. It becomes A bar. Here this becomes B bar. Similarly at this side, this becomes C bar. This becomes D bar. So NAND logic is what? A bar, B bar is inside. As A bar, B bar as A bar, B bar are given as input. That means here you will be getting this as A bar dot B bar. Then the whole bar. That is the logic of this NAND, right? Similarly, here also it is C bar dot D bar, the whole bar. So when you have this kind of bar, okay, that is A bar dot B bar, the whole bar means if you take the bar, then it becomes A bar, that is A double bar. This operator changes to plus. Similarly here, B double bar. So A double bar is A, B double bar is B. So this is equal to A plus B. The same way, here you will be getting this as C plus D. Okay. So these are the outputs of this gate number. You can take this as 3 and 4. And if you take this as 5, these are inputs to this fifth NAND gate, right? So this A plus B and C plus D are the inputs to this gate, this NAND gate. So whenever they are the inputs, what would be the output available at this point? It's nothing but A plus B dot of C plus D, the whole bar. That would be available at this point. Okay. After that, again you are going for this inversion or NAND gate, right? So you will be getting double bar. So whenever you get the double bar, you will be getting the values as A plus B dot C plus D. Okay. Double bar means it get cancelled actually. So you will get the output like this. Okay. This is how it is being implemented. Okay. Thank you.